So that first method is slicing. And so what we have to do then is we have to have a figure to use this method so that every slice of it that you might take, either perpendicular to the x-axis or perpendicular to the y-axis, is always the same type of shape with the same, it's a similar triangles, or they are all similar circle. I mean, circles are all the same. They're all circles, or they're all like squares, or they're all similar rectangles, or they are all something like that, similar trapezoids. And so what we do is we find what the area of one typical cross section, so just one arbitrary cross section of it, we find what the area of it is in terms of x or in terms of y, and then we just integrate across the entire whatever coordinate piece of the coordinate system that we're using for the particular thing. So remembering that our integral is just a summation, so really all we're doing is we're summing together all these infinitesimally thin little slices. Really, it's the area times the thickness of the slice. The a of x is your area, and the dx is the thickness of each slice. So really, you're summing together a bunch of tiny little volumes, area times thickness, to come up with the exact volume of the solid. So let's take a look at one here, a nice simple one to start with. We've got the base of a solid is the region between this curve y equals 4 root sine x and the x-axis from 0 to pi. So 4 root sine x just looks about like that from 0 to pi. And the information that we are given is that the cross sections of this are squares, and the bases of them run from the x-axis to the curve. So effectively what we've got here, that looks absolutely horrible, is a bunch of squares sticking out of this curve. I got some very small ones over here sticking up out of here, and everywhere along perpendicular to the x-axis there is a square cross section. So if I sliced it vertically and opened it up, the face of both sides of it would be a square. Does that make sense, everyone?
Yes.
Okay. So all we have to do then is figure out what is the area of one of these typical cross sections, and then we just put that into our integral. So we're looking for the area of one of the squares. So what is the area of one of those squares? Should be a side length squared, right? What is the side length?
Y.
Yeah, it's just y. So our area is y squared. So we could write this, if we wanted to, initially as y squared inside of here, but we're going to have to do some work to convert that because the thickness of each of those is in the x direction, right? They're very thin, they're sliced perpendicular to the x-axis. That very tiny thinness is in an x direction. So this is an integral of y squared dx integrated from 0 to pi. Everybody good with that? Everybody good or no? All right. So what do we turn the y squared into then?
16 sine x.
Yep. We'll just square the 4 root sine x. I'll just write 4 root sine x to start with. Pull the 4 squared out. 16 times the integral from 0 to pi of sine x dx, which gives us what? 16 times, or negative 16 cosine x if we want to. Put the 16 back in. From 0 to pi. And what does that give us? What's the cosine of pi?
-1.
So we got -16 times -1 minus -16 times 1. Cosine of 0 is 1, right? So what do we get?
32.
32 units cubed. Good or no?
When we change from x to y, we don't have to change the limits of integration, right?
Oh, yeah, sorry. I should have written that those were x values there since I had two different variables there. Just specify what variable you're using.
Okay.
Since we're converting it all into terms of x, we want the limits of integration as well as our dx to be x's, as well as our integrand itself, the y squared, needs to turn to x. So that's why we didn't change those, because we'd originally already had those x values. Good.
Yeah.
All right. Okay, let's do another one. Same function, 4 root sine x. Still 0 to pi, but this time the cross sections are equilateral triangles. So yeah, equilateral triangles, bases are running from the x-axis to the curve. Okay, so they're perpendicular once again to the x-axis. And so first thing we need to do is figure out a formula for the area of each of those triangles. And what is the area of an equilateral triangle?
√3 times the base, like squared. Yeah. No.
Side squared times √3 divided by
2.
divided by 4. Right? This is a formula for the area of an equilateral triangle, but it might be good for you to know. Side squared √3 over 4. And so our side here, each one is equal to y, the value of the function. So that's going to give us, if we square y, 16 sine x √3 over 4, or 4 √3 times sine x. And so our integral will become 4 √3 times the integral from 0 to pi of sine x dx. Everybody good with that? No. Everybody good with that or no?
Yep.
Any questions on that? All right, let's do another one. This time we've just got the function sine x. And we're talking about one arch of sine x, so that'll just be from here to here, which is 0 to pi. And our cross sections are what shapes this time?
Semicircle.
Yeah, you got semicircles. So what's the area of a semicircle? It should be 1/2 pi times the radius squared, right? And what is the radius?
One half y.
What?
1/2 of y, or 1/2 of sine x. So what does our full area formula come out to be?
One 1/8 pi sine squared x.
Exactly. So this is 1/2 pi times 1/2 sine x squared, which gives us a 1/8 pi out in front. an integral from 0 to pi of sine squared x dx. Everybody good or no? All right. What about our integral of sine squared x? Sine squared x should become a 1/2 out in front, right? So pi over 16 times an integral from 0 to pi of 1 minus cosine 2x. Everybody good with all this or no?
Yes.
All right. What's our integral of 1 minus cosine 2x? Should be x minus what?
Half sine 2x.
Good. And then what? What do we end up with here? Pi over 16 times pi minus 0, right? And then minus 0 minus 0. Or pi squared over 16 units cubed. Good or no? You guys are awfully quiet today.
Inches cubed, right?
Oh, were they inches? Did I say inches in there? Oh, I did say inches. All right, sure. Inches cubed. Perfect. All right, everyone's good with these? Yeah? We'll do one more of these.
Sounds good.
All right. So we've got the base of a solid is this disk that is x squared plus y squared equals or is less than or equal to 1. So it's just the circle with the radius of 1. And the cross sections are perpendicular to the y-axis now. And they are isosceles right triangles with one leg in the disk. So there's my right triangle, and these two sides are the same, right? And we want to find the volume. So we need a formula to represent the area of each of these triangles. So we know that the area of a triangle is 1/2 base times height, right? And we know that our base and our height are equal to each other. So we could just call that 1/2 base squared. And what is our base equal to?
Would it be 2x?
It'd be 2x, right? From the origin to wherever we go over here is x, right? So this should also be x. Our base will be 2x. So that will make this 1/2 of 2x squared, or in total, 2x squared, right? Everybody good with that? Okay, so now we're going to integrate, but since we've got our cross sections are perpendicular to the y-axis, that means that these have a very small thickness in which direction?
Y.
In the y direction, which means that they have to be done in terms of y. And we're going to integrate from y equals -1 to y equals 1. And we've got 2 times x squared dy, which means we've got to deal with the x squared, right? And so what does x squared equal? Should just be able to go back to our original problem. X squared is equal to 1 minus y squared. And we should end up with 2 times the integral from -1 to 1 of 1 minus y squared dy. Or 2 times y minus y cubed over 3 from -1 to 1. Or 2 times 1 minus a third minus -1 plus a third, which gives us what? That's 2/3 plus another 2/3, 4/3 times the 2. And this time I don't think I gave you specific units, so we'll call it 8/3 units cubed. Good?
Yeah.
All right. Cool. Everybody feels like they remember how to do cross-section, area, volume problems?
Yeah, I feel like I remember.
Oh, good. All right. Let's take a look then at this one. We're going to take the region between the x-axis and square root of cosine x from 0 to pi over 2, which is what I've drawn here, and revolve it around the x-axis and find the volume of the new solid that is given. So if I revolve this around the x-axis, I'm going to have a three-dimensional little, I don't know, bottom of an acorn looking kind of thing here, right? And what are the cross sections of it if I slice it vertically here?
Circle.
They should be circles. And anytime we do this revolution around an axis, we're going to end up with cross sections that are circular. So they're circular, and the thickness of each one of them, as I slice them to get those circles, I have to slice it perpendicular to the x-axis, which means that we're going to do this all in terms of x. And so now when we look for the area of the cross section, it's pi r squared, which gives us pi times our radius. And what's our radius? It's the distance from the function to the x-axis. Right, that's r. And what does r equal?
Square root cosine x.
Right, it equals y, which is square root cosine x. So this is pi times square root cosine x squared, or just pi cosine x. Good or no?
Yeah.
And so our integral will be pi times the integral from 0 to pi over 2 of that cosine x dx. Or pi sine x from 0 to pi over 2, which is pi minus 0 or pi units cubed. Good?
So good.
Great. So we'll recognize that these revolutions always give us cross sections that are circles, and so that we'll always just do the area is pi r squared for those cross sections, multiply it by the dx or the dy, depending on which way we rotated. Anytime you rotate around the x-axis or something that's horizontal, it'll have to be done in terms of x, and anytime you revolve around something that is the y-axis or vertical, you'll want to do it in terms of y. All right, let's take a look at another one. We got 2 plus x cosine x from negative pi over 2 to pi over 2. So something like this. It's not perfect, but could be a lot worse. It's going to look something like that. Everybody agree if we revolve that around the x-axis, and we're going to get like a vase looking thing or something sort of? Great, okay. So it should be pi times the integral from negative pi over 2 to pi over 2 of the radius squared. And what's our radius?
2 plus 2 2 plus x cosine.
2 plus x cosine x squared dx. And if we wanted to, we could do this by hand. I'm not gonna force you guys to do this by hand, but you should know how to. If you distribute that all out, you're gonna get 4 plus 4x cosine x plus x squared cosine squared x dx. And that's going to be a little bit of a pain. The 4 is easy enough to get your 4x, right? But the 4x cosine x, you got to do by parts. And the x squared cosine squared x, you'll have to do power reducing and do parts of it by parts. But we can just use our graphing calculator to tell us what this integral is and make sure that you are in radians. So let me know what you got. Sorry, I didn't see those in the chat there. 41.070 units cubed. Everybody good with that?
Yep.
All right. All right. Let's have you guys do this one on your own. Set this one up and evaluate it. You can use your calculator to evaluate it if you wish. You could integrate this by parts if you wanted to, but it's all right if you just use your calculator for it for now. So I'll give you guys 2 or 3 minutes, maybe probably 2 minutes is more than enough. So I'll give you 2 minutes to read through this one, sketch a little picture, and tell me what you get. Ready, go. All right, so you probably graphed this because you probably didn't know exactly what the graph of x inverse tangent or the square root of x inverse tangent of x looked like. And we were looking just from the part from 0 to 1, which looks something like this. Maybe a little more curves than that. It's also got a piece over here, but the only piece we care about is the piece on this side. So here's 1, and we end up again with this little acorn looking thing. Everybody agree with that? That's what your graph looked like, hopefully. And your area, once again, was pi r squared with r equal to the square root of x inverse tangent x. So you had pi times an integral from 0 to 1 of x inverse tangent x dx. Is that what you all set up? Or no?
Yep.
And what'd you get as your answer?
0.897.
Perfect. 0.897 units cubed. And should be good. Any questions on that?
Why does it say the region bounded below the x-axis? Oh, below by the x-axis.
Below by the x-axis, yes. Bounded by the x-axis on the bottom of the region.
Yeah, I don't know. That kind of threw me off for a second because I was like, none of that is below the x-axis. But I see now.
Good. Yeah. Sometimes the wording on those makes it sound a little confusing, but hopefully not too bad. All right. So what happens then if the region that we are revolving is not pushed up fully against the axis that we're revolving it around? So we look at the ones we just did. The region was revolving around the x-axis, and we were completely touching the x-axis in our entire region, right? The entire region is pushed up against the x-axis here that we're revolving around. Same thing here, it's completely pushed up against it. That's a different type of problem, right? So sometimes the region that we're revolving, for example, this region between y equals x and y equals x over 2, might not be fully pushed up against that x-axis, right? There might be a gap between it. we still want to know the volume if we revolve that region around the x-axis. So what does that do? It gives us, that's really bad. That's better. It gives us something like this, where we've now got this outer piece with a cone sort of pulled out of the middle of it. We all sort of visualize that, hopefully.
Yeah.
Okay. And so what do the cross sections look like now? They look like washers, right? These are washer cross sections. Right? They're little rings, right? And they still have a thickness to them, right? These are, remember, these are three-dimensional things, but they have an infinitesimally thin thickness. In this case, since we're slicing it vertically and we're revolving around the x-axis, that is in terms of x. And so all we have to do is find the volume of the outer piece and subtract the volume of the inner piece, or pi times the outer radius squared minus pi times the inner radius squared dx integrated from lower limit to upper limit. Okay. So we're just doing the volume of the outer piece minus the volume of the inner piece, or the area of the outer piece minus the area of the inner piece times their thickness, and then summed together. Good or no?
Great.
All right, so what's our outer radius here?
X.
Yep, and what's our inner radius?
X over 2.
Good. And so we'll just put this all in. Pi times the integral from 0 to 5, right? Yep, 0 to 5 of our outer radius squared minus our inner radius squared. And we could definitely rewrite that as pi times the integral from 0 to 5. What's x squared minus a fourth x squared? That would be 3/4 x squared. And now we just integrate and evaluate, and we're done. So what do we get when we integrate it? Pi times x cubed over 4 from 0 to 5, which ought to be 125 pi over 4 units cubed. Good or no?
Pretty cool.
I agree, pretty cool. All right. You guys will do this one on your own. I will give you 2 to 3 minutes to work on it. Ready, go. All right, so we knew it should be pi times an integral, right, of our outer radius. What's our outer radius?
Cosine X.
Cosine x, and we got to square that. Minus our inner radius, and we got to square that, which is sine x. So sine squared x. So cosine squared x minus sine squared x dx. And we also have to find our limits of integration. We know we're going from 0, we're talking about the region in the first quadrant, and to wherever they intersect. And so we'd note that sine x equals cosine x when x is pi over 4. That'd be their first intersection point. So we got pi times the integral from 0 to pi over 4 of cosine squared minus sine squared. And what's the best way to do that integral?
Power reduce both of them.
No.
It's a double angle.
Yeah, it's a double
identity.
angle. Pi times the integral from 0 to pi over 4 of cosine 2x dx, right? You come out to get the, I think you get the same thing if you do the power reducing, but I mean, you get it. I don't know what you actually get something different. What's that? 1/2 times 1 minus cosine, and 1/2 times 1.
Yeah, you get the same thing.
You get the same thing. Yeah, you should get the same thing. But it's probably easier if you just write it this way. And so what is that integral? What's the integral of cosine 2x?
One half sine 2x.
Mm-hmm. From 0 to pi over 4. Good or no? And We got pi times, and then what's the sine of pi over 2? 1/2 the sine of pi over 2 is just a half. And then minus what? Minus 0, right? And so you get pi over 2 units cubed. Good or no?
Yeah, it's great.
Wonderful. All right, let's do another one. We've got the region between root ln x and ln x is revolved around the x-axis. So first off, we're going to need to find some limits of integration. How do we find the limits of integration?
Set them equal to each other.
All right, so root ln x should be equal to ln x. And when does that happen? If x is,
Is it 1 and e?
yep, x equals 1 and x equals e, right? If x is 1, those are both 0. And if x is e, they're both 1, right? So we're going to have pi times an integral from 1 to e of the outer radius squared minus the inner radius squared dx. The question, though, is which one is the outer radius and which one is the inner radius? Which one is above the other on the interval from 1 to e?
ln x.
Ln x is above root ln x? Is that what you said?
Yeah, I think because it's increasing faster.
Let's be careful. If I put in something between 1 and e, right, natural log of 1 is 0, and natural log of e is 1. So that means effectively, I'm putting in something between, the value of ln x is going to be something between 0 and 1. And what happens when you take the square root of something between 0 and 1? For example, what's the square root of 1/4?
1/2.
It gets bigger, doesn't it? Or the
Yeah.
square root of 1/9 is 1/3, right? It gets bigger. So if you take the square root of something between 0 and 1, you actually get a larger value than you started with. And so therefore, on this interval between 1 and e, root ln x is actually, x in here, is actually above ln x. Everybody okay with that? Does that make sense? Yes, no, maybe?
Yeah.
All right, and we remember the integral of ln x is x ln x minus x, and we remember that we could do this one by parts. We did both of these integrals a couple weeks ago. So we'll just use our calculator now to approximate that. What does that come out to be? What does that come out to be?
Zero 0.885 units cubed.
Sounds good to me. Y'all got that? Hopefully. I didn't actually check it, so hopefully that's right.
Yeah, I got that too.
Great. All right, let's do another one. we got, no, that doesn't look good. Let's make sure we got the actual fraction bar there. So we've got, it's bounded by 3 root x over 4 in the x-axis and the line x equals 4. So we're bounded here also. And we're revolving around that line x equals 4, which means we're actually going to get something like this. And now if we slice it vertically, what do we end up with?
Bad stuff.
Right, we end up with bad stuff, right? But if we slice it horizontally, we should end up with circles, which is good stuff, right? Okay, so we've got some nice circles if we do it in terms of y, which means everything's got to be done in terms of y. And then we've got to have pi times the integral. Let's see, what are our y values? We're starting at the bottom here, which is 0, and going up to here. What's that y value up there when x is 4?
3.
Should be 3. Okay. And then what? We need a radius inside of here to square, don't we? What's our radius of any of these circles? Let's say from here to here. That's our radius. What's this distance?
It's x, but we would like want it.
Well, no, this distance right here is what? From 0 to here is 4. This distance will be our x, right? So our radius ought to be 4 minus x. And then what do we have to do with that? You're going to say something, I think, Noah.
Put it in terms of y.
Put it in terms of y. And so if r is 4 minus x, we just need to figure out what x is in terms of y. If y is 3 root x over 4, that tells us that x is what?
Four y squared over 9.
4y squared over 9. Sounds good to me. So we'll put that in for our x. We got pi times the integral from 0 to 3 of 4 minus 4y squared over 9 squared dy. And this one's a pretty nice simple one to do. So maybe we just distribute that one out and get an answer. Or you guys want, whatever, it doesn't matter. You guys want to just approximate it? Let's just approximate it. What do you get if you approximate that?
I got a 80.425.
80.425. You guys all agree with that?
Yep.
Cool. All right. Last one. I'll let you guys work through this one on your own. It's the last one we'll do today. And then we'll talk about cylindrical shells tomorrow and start talking about arc length tomorrow. All right, ready to go. All right, so first off, hopefully you sketched a graph of this, right? So there's ln x, there's x equals e, right? And we're taking that and revolving that region between that and the x-axis around around the y-axis. So we're going to end up with like a sort of washer type thing sitting over here, where we've got, you know, these weird little discs that we get over here, that we only get if we slice it horizontally, right? And so let's label a few things in here. We know that's the line x equals e. So what are the coordinates of this point? Is there e comma, since it's natural, it should be e comma 1. Okay, that'll be helpful to us because we know we have to integrate this in terms of y, and we have to go from the bottom, which will be 0, to the top, which will be 1. And we know that this is going to be pi times something, right? So the outer radius is from the y-axis out to the furthest out we go, right? What is the outer radius always equal to?
E.
Should always be e, so that should be e squared, right? That's our outer radius of e. And what's our inner radius?
X.
Okay, how do you get x? From here to here, right? Call this our inner radius. That's x. And so we have to have x, though, in terms of y. And so if y equals the natural log of x, then e to the y is equal to x. So this ought to be minus e to the y squared, or e to the 2y. Good? Everybody agree with that?
Yeah.
All right, and the integral of e squared is e squared times y. And what's the integral of e to the 2y?
Is it 1/2 e to the 2y?
It should be 1/2 e to the 2y. And so now we just have to evaluate that from 0 to 1, which ought to give us what? The first one should be pi times e squared minus e over 2. And then minus pi times 0 minus 1/2. Everybody agree with that? Which should give us, we got e squared minus e over 2, and then plus the 1/2, right? So it's pi e squared minus pi e over 2 plus pi over 2 units cubed. Everybody good there? Any questions, any issues there?
Why wouldn't it be minus e squared over 2?
Minus e squared over 2. Oh, because I don't know how to multiply 2 times 1, apparently. So there we go. Good? Better now? So we could combine those. Pi e squared minus pi squared, or pi e squared over 2. Darn. Now I feel like I should write this on a new page. What does that become? It should become pi e squared over 2, right? Plus pi over 2. Does that look better to everybody? Any questions, any issues with that? All right, that's it then.